there was some question at the break about this old problem, which I can also relate to the new problem, so I'm going to touch on that at the same time. This new problem consists of a nozzle that's vertically placed, and gravity is not to be neglected this time. It didn't say anything on the problem statement to neglect gravity. Furthermore, the nozzle area are given. And pressure is also given at the base. So let me deal with the pressure force. First, the nozzle exit to ambient is a pipe at station 1. I want to compare that with the cone that you did for your homework due today, which is an air jet hitting a cone with a certain weight, and then that gets diverged asymmetrically. All right? So what is the pressure at the base of this open air jet in this old homework problem? What is the pressure here at station 1? This is an open air jet. And what is the pressure after it's split off on the cone? Atmospheric. Do you get it? It's a free jet, open to atmospheric. Contrary to that, I have a pipe, a tube, plumbing, that is containing the water inside. Can the pressure inside here atmospheric? No. It has to be higher. And you're told in the problem statement is 40 kilopascal. And that is the pressure needed to push the flow to come out from that nozzle. So an open jet versus a contained plumbing is totally different. The pressure inside this plumbing is anything but atmospheric. And you either have to calculate that, maybe use Bernoulli, or it has to be told. All right, so make sure you understand all those details. Okay. So what I want to alert you to is the fact that the size of this nozzle, when you look at the area, it doesn't really allow you to have a grip of it. The area at the exit is 0.01 meters square, and the intake at 1 is 0.02 meters square. Let me translate that to you in size of centimeter. So all of a sudden you have this pipe that is 12 centimeter diameter at the base, 6 centimeter at the top. So it's a pretty sizable piece of plumbing. And the water contained inside is also fairly big in volume. Prior to this, you have done a homework of which you also have to account for the body weight. And it turns out for that previous problem, they are negligible because of the size. Do you think you can neglect all this weight for this problem? This big plumbing, and the water contained in this plumbing about this size. Do you think from engineering standpoint, do you think it's negligible? Well, why don't you find out from the homework? Right? The answer is no. But aside from that, the mechanics of this is reasonably straightforward, and I think you should be able to, if you can do the homework due today, you should be able to do this one as well. All right. The second problem is a thrust reversal on an engine, aircraft engine on landing. So what happened, and you have seen this when you fly around the country, you know, as soon as the landing gear touches the ground, a deflector is immediately deployed and take the exit jet and reverse it so that it helps as an air brake to change the momentum of the the jet, or the plane rather, to slow it down. So you have now the 2D momentum equation that you need to apply. It seems peculiar area 2 is not given, but no panic. Turns out if you do the momentum equation carefully, that area is not needed. I will leave you at that. But the momentum equation is fairly straightforward. It's actually a 1D problem because the only thing that is of concern to you is the x direction. All right? So you may have an accident that caused the plane to crash on takeoff. On takeoff, this device recorded by mistake. And obviously the plane couldn't take off and it crashed. A mechanical failure. Yeah. Yes?
What did it say after A2?
Not given, sorry. Yeah. You know, sometimes you may think that to get the full unique rho V A, but I'm just pointing out the fact in this problem statement the area is not given. But it turns out you don't need it. You can still solve the problem. Okay. All right, any question on the XY momentum equation? I am actually slightly ahead of my schedule, so I'm going to spend the remaining 10 minutes on the random transport theorem. Now applying to the momentum equation. So let me revisit the transport equation. Which we have applied that to continuity, and now I'd like to do that for momentum. And next time when we come back, I'd like to use some analogy to read this momentum equation in the physical term. So this is the general random transport theorem. And all the nomenclature has been dictated before. I'm not going to repeat that. For continuity, this is another repeat. We have shown that I was able to reproduce the continuity equation I spent so much time on using this water tank problem. We painstakingly, using this problem, start with first steady problem, talk about the significance of this dot product of velocity perpendicular to the area, all lump into one term so that the in and out mass flow rate are all accounted for. And then we generalize this to an unsteady problem where the height is changing. And then we have this term, and you can read this all in plain simple English. Now on that basis, I'm going to introduce the momentum equation by setting a new variables or nomenclature. So now I have to reset the B, which before was the mass. Now I'm doing momentum, and I'll give you the answer straight out. I'm going to set the capital B to be my momentum flux, m times the velocity. Oh, I'm sorry, I misspoke. This is linear momentum, not momentum flux. This is simply mass times velocity, a linear momentum. With that, and I use the overhead because this is now a vector, right? Not a scalar-like mass. This is directionally dictated per unit mass is simply now the velocity vector v. So far, so good? For my system equation, I can revert this linear momentum into something I'm more familiar with, which boils down to m mass times acceleration, or in vector acceleration. So from Newton's law, what is m times acceleration equal to? Force, very good, but summation force, all forces. Also, make sure it's the vector. So now I'm in a position to use Reynolds transport theorem, which is stated in here. I'm just going to replace all those variables. Now apply to momentum in this equation and see what comes out. So in doing that, I have forces on the left. That's the rate of change of this term here for the system, which we convinced that is equal to the force. And then steady term, and then the remaining term, which is being dictated by the Reynolds transport equation. So I have now, through the deduction of the Reynolds transport theorem, a new momentum equation that looks very different than what you have seen before. How different? Well, what we have been using prior to this is fx, just like the 2D plate problem. This simple formulation, or Fy replacing the u by v. This pair of equations is what you have done for all the homework and all that I needed for the 2D plate problem. Are they equivalent? This is the most general form of the momentum equation. Can you see any resemblance between this pair equation and this one? And can you draw a parallel between this equation for momentum and compare that with continuity? And from that comparison, can you read to me, with the help of this pair equation, the physical interpretation of the momentum equation? What does the term here mean? What does the term here mean? Can you do that for continuity? First of all, if I give you a quiz problem or the test problem and I say, read this continuity equation to me in plain, simple English, what is this term? And what is this term? Can you do it? Think of this diagram. And same token, if I ask you to read this equation to me in plain, simple English, can you do it? Think about these two equations as a pair, and think about the example we did in class. And next time, I will show you how to read that in plain, simple English. Okay?